Thanks everyone for coming. The last people who endure 3 weeks in a row of French people talking about isotopes. So I promise it's the last Frenchman to hear about isotopes for a while, hopefully. So it's great to have Auguste here. So Auguste is doing his PhD, so he's currently doing his PhD in Lyon at École Normale Sup, so ENS Lyon. And he's really brave to give us a seminar across the world, not because they're mean, just because it's great that you do. I guess it's I'm sure you got into this because you like dinosaurs as a kid, right? So I think it's great to see sometimes you're passionate about something as a kid and you actually make a PhD out of it. So Auguste is going to talk about isotope, but applied to dinosaurs. Yay! Floor is yours.
So thanks for the introduction. So I'm really happy to be here to talk to you about my work. So I will mainly explain you our recent published study about resource partitioning in Cretaceous faunas. And I will also explain you briefly why I am here in Australia for a few months at the end. And so in this study, we focused our attention on 2 faunas. And so I will explain you what fauna it is. So fossils that we studied came from Morocco, from the Kem bed deposits, and also from Gadoufawa, a fossil deposit in Niger. So Kem beds are a large fossil deposits that include several small localities with some fossiliferous layers inside. So here fossils that we studied came from 4 of these localities that are located at the east of Morocco, close to the border with Algeria. So in Kem bed, the landscape looks like that. So you have some Cretaceous deposits, and in some part on some cliffs, you have some fossiliferous layers where you can find some really interesting dinosaur fossils, but also turtle fossils, fish fossils, a big variety of fossils. And at Gadoufawa in Niger, the context is a bit different. The fossil deposit is really huge. It's like several hundred of kilometers, and it's located at the center of Niger. The landscape is also a bit different because it's completely flat on this area, because everything is eroded by aeolian erosion. And in some part of this landscape, sometimes you have fossils emerging at the surface that have been excavated thanks to the erosion, and sometimes really interesting fossils, because you can even find some dinosaur fossils that are in anatomical connection or subconnections. So it's really a great field of study. These 2 fossil deposits are not dated exactly in the same period of Cretaceous, because Kem beds are dated of the beginning of the Cenomanian, at least for the 4 localities that we studied. And whereas Gadoufawa is dated between the Aptian and the Albian, so around 113 million years ago. So the dates are different, but why did we decide to study both of these fossil deposits? Is that it's because they have some things in common. And so what they have in common? Indeed, both of these deposits exhibit a similar composition of fauna with similar groups of animals inside. So with similar groups of herbivorous dinosaurs and similar group of fish, and also with similar group of predators with non-spinosauric theropods. So if you are not familiar with this concept, non-spinosauric theropods you can imagine a T-Rex-like dinosaur, basically, and with also some crocodilomorphs. So crocodiles that could be really huge for some of them. For example, at Gunflower, we have the Sarcosuchus imperator, which is one of the biggest crocodiles that have ever existed. This animal can reach 15 meters long, so it's really a big animal. And we also have some spinosaurids. So spinosaurids are a part of the theropods family, but they have a really peculiar morphology with an elongated snout that, for some aspects, look like to crocodile snout. And they have a really peculiar ecology that are really debated among the paleontologist community. So these are the three major groups of predators that you can find in these faunas. And another thing that these two faunas have in common is that we observed an inverted trophic pyramid. So that means that we found a lot more fossil remains that come from predators than fossil remains that come from herbivorous dinosaurs. They are most likely prey in the classic model of how works continental fauna in Cretaceous. So this is really weird because what we could expect is a classic trophic pyramid with decreasing of abundance from the plants to the tertiary predators, with the primary consumers and the secondary consumers in the middle. And this is how works modern continental faunas. And this is due to physiological processes. It's just due to the fact that when an organism eats another thing, this organism does not gonna absorb 100% of the energy of its food. So due to this lack of energy, at each step of the trophic level, you decrease the abundance of animals, of biomass in general. So it's really unlikely that it was different during the Cretaceous. So to understand why we have this inverted trophic pyramid in these faunas, some authors advance the idea that it could be a broken pyramid, which is just a missing part of the puzzle to understand how were the trophic structure of these faunas. And one of the most likely possibility is that this missing part was indeed fish, because if you include fish as potential prey for predators, it makes the trophic pyramid look a normal shape. And so that means that the predators of this fauna might be at least partially piscivorous, and so that the ecological, the trophic structure of these faunas was a bit different than what we can expect of other continental faunas. So not just herbivorous dinosaurs are potential prey. So this hypothesis is supported by different studies, including study of abundance of fossil remains, because if you look just at dinosaurs, you have an overabundance of predators, but if you look at the whole fauna, you see that there is a lot of fishes in this fauna, because we are talking about continental faunas, but they are for fluviatile deposits, so that includes a lot of fossils from fish, but also of turtle and crocodiles. And so this supports the idea that fish were part of the trophic pyramid for these predators. And there is, if we compare with other faunas, so this one was in Kemkem beds, and if we look at the Béchar fauna in Algeria, which is not one of the faunas that we studied, but which is a fauna that are similar features than the two faunas that we studied, we see that this time again there is a lot of fishes associated with a lot of theropods, and especially we see here that the Spinosaur abundance is correlated to the abundance of fishes. So that's here a clue that Spinosaur might be piscivorous, but still with this data, we can't tell, we can't describe precisely the trophic links between the species of this fauna and the overabundance of Spinosaur relatively to the other pteropods may be just a difference of environment preference and not of direct differences. So we still need to investigate that more deeply to really understand the trophic structure of this fauna. And we also need to, if we want to talk about resource partitioning among predators, to explain how they were so abundant in this fauna, we also need to quantify it, which is not possible with this data. So this is the goal of our study, is to describe the trophic structure, but also to quantify the diet of the different predators of this fauna. And so I will briefly describe the method we use. So we use calcium isotopes. You might be a bit familiar with it if we saw the talk of Theo a few weeks ago. So here are the four major stable isotopes of calcium. In our case, we use calcium 42 and calcium 44. And so we measure the isotopic ratio between these two isotopes that we normalize on a standard. So this normalized isotopic ratio, we note that as a delta calcium, which is the notation that you're going to see in the rest of the presentation. And so why we use calcium to understand trophic structure is that it's because calcium isotopes are an innovative trophic proxy. I will explain you that in detail just now. So what was the trophic structure of this fauna? So according to data on modern faunas, there is a relation between the delta calcium and the trophic level, both in marine and terrestrial environments. You can see here that you progressively decrease the delta calcium from the initial intake of calcium in the environment. So here seawater for marine environments and soil for terrestrial environments. And you decrease the delta calcium from this point to tertiary predators, to tertiary consumers, with herbivores at this point, secondary consumers at this point, and so the top predators that you know. To schematize that, we could take a plant with a given isotopic composition for the calcium, and then if an herbivorous animal eats this plant, he will have a blood and bones that will have an isotopic signature that will have a lower delta calcium than the plants, than the plant he eats. And with the same way of functioning, if we consider this herbivorous animal as a potential prey, if this animal is eaten by a predator, the blood and the bones of this predator will also have a lower delta calcium than its prey. So here we have what we call a trophic signal, is that at each step of the trophic chain, you decrease your delta calcium. Using that, we can reconstruct the trophic pyramid with plants, primary consumers, secondary consumers, and tertiary consumers, just by using calcium isotopes. So it's a really promising tool for that. But here it works for modern faunas, but we really could use that for fossils also. So to use that for fossils, we need to deal with diagenesis. So diagenesis is the chemical alteration of fossils during time. And hopefully, so here we choose to work on enamel, on fossil enamel, which is a material with really low porosity. So due to this low porosity, this tissue is really unlikely to be alterated through diagenesis. And calcium is also highly concentrated in enamel, so that means that if you want to overprint the original isotopic composition of the enamel, you need to imply extensive diagenetic process with recrystallization, for example, and we have some methods to detect if this process has occurred or not. So that's what we done on our student fossil. We test if there were some recrystallization, and because there were not, we decided to pursue the study and to apply some calcium isotope measures. And these are the results that we obtained from the Gaduflower fauna. So here we can observe several things. First of all, we see that herbivorous dinosaurs, so here 1 and 2, have the highest delta calcium of the dataset, and that predators associated with this fauna, so here in 3 you have the non-spinosaurid theropods, in 4 you have Sarcosuchus imperators, the giant crocodilomorph, and in 5 some spinosaurids. And you can see that all these predators have a lower delta calcium than their potential prey. And another interesting thing to observe here is that these 3 predators have a distinct clustering. So that means that these 3 predators had a different ecological niche associated with a different food sources or a different proportion of food sources. So this is an indication that there is a resource positioning between these predators, and that all these predators do not forage on the same food sources with the same habits. If we look at that on the chemical bed fauna, unfortunately we had less fossil to study on this fauna, but still we observe similar features with distinct position between non-spinosaurid theropods and spinosaurids. And here crocodiles have a similar signature than non-spinosaurid theropods. So here also in both faunas we have this distinct clustering and a similar trophic organization, even if for the chemical bed we don't have enough data to go as further than we can go with the Gaduflower fauna. So now we think that thanks to this data, we know that there is a resource partitioning, but we still need to quantify the diet of these predators. So that's why we did also by using calcium isotopes, because thanks to a property of calcium isotopes, in modern vertebrates, we observed that there is a constant offset between the food of a vertebrate and the isotopic composition of its bones, with a difference of minus 0.57 per mil. And because this difference is constant among all modern animals that we analyzed yet, this is likely that the difference was the same for archosaurs, so including crocodiles and dinosaurs. So that means that we can use this offset to identify the isotopic composition of the food of predators from their own isotopic composition for the calcium. So we just need to, by knowing that, we need to know the isotopic composition of the potential food sources of these predators, and then by a comparison of its theoretical food sources and the available food sources, we can make a diet model. Because we can do that because when a predator eats another animal, he only need 1% of bones in its diet to change its diet isotopic signature as to be equal or almost equal to the one of bones. So that means that just a few percent of bones are needed to overprint completely all the rest of the food signature. And so that means that we can use the isotopic signature that we collect on bones on enamel, because enamel have the same isotopic formations as bones. So we can use the data that we collect on fishes, enamel, and herbivorous dinosaurs to have the information to identify which food sources were the sources of the predators of this fauna. So that's what we did by building a simple diet model. So here we focused our attention on the three major predator groups, so non-spinosauride theropods here, crocodiles here it's Sarcosuchus imperator, and on Spinosaurids. So by taking this predator one by one, we can see that the fish intake that we can estimate for non-spinosaurid theropods was between 0 and 30%. So that means that these predators were foraged mostly on terrestrial prey, so on herbivorous dinosaurs. And if we look at Sarcosuchus imperator, fraction of fish are a bit different because they are between 0 and 58% of fish. So it's likely that Sarcosuchus imperator have a more mixed diet between terrestrial prey and fish prey. And finally, if we look at Spinosaurids, the range of fraction is quite large because it's between 0 and 100%, so all the possibilities are possible for this group. But if we look at closely, you can see that here a majority of specimens are located at in the lower part of this population. So at this point, that means that a majority of the spinosaurids that we studied were at least partially piscivorous or even completely. This is due to the data that we collected on sources. When you have an isotopic composition that gives information that your animal was at least partially piscivore, this is equal to say that it could be also 100% piscivore. So we can't make the split between these two hypotheses, but still that's a good information to say that these spinosaurids were mostly piscivores. So in conclusions, we have a clear resource partitioning among predators of this fauna, with non-spinosaurid theropods that were mostly carnivorous, whereas spinosaurids were more piscivorous oriented. So this resource partitioning between these predators is likely to have buffered the competition between these groups, and it might be a key to understand why predators are so abundant in these faunas. And this result also supports the piscivorous habit of spinosaurs, because thanks to our data, it's put this group as a more potential piscivorous predator, and with isotopic composition that is compatible with a piscivorous diet. So to go further, this study opened great perspective on the study of the feeding habit of spinosaurs in the rest of the world and in the rest of the time, because spinosaurs are a group of highly debated ecology. So it will be really interesting to see if this piscivorous habit is widespread or just specific to few faunas in the fossil records. And more generally, this study opened great perspective to study the evolution of trophic structures in the deep time and of diet, with a first step to reconstruct quantitatively the diet of long extinct animals. You saw that the fractions that we estimate from our diet model are quite large, but still, few decades ago, it was science fiction to have an estimation like that of a diet for animals that were extinct so long time ago. So that's still really interesting and promising. But we still have a lot to learn about calcium isotopes, because calcium isotopes are something relatively new in the field. And so the aim of my PhD is to understand if the reproductive physiology could explain a part of the intra-specific variability of calcium isotopes, because you saw that inside a species there is some variability of isotopic composition, and so a part of this variability might be due to the reproductive physiology, and the aim is, the main question is that could we identify reproductive strategies using calcium isotopes? For example, there is apparently a link between lactation and calcium isotopes. There is data collected on modern sheep groups that shows that there is a difference between male and female inside the sheep population that might be due to the lactation. And there is also, this is the work published by Taylor last year, which shows that we can identify some breeding practices using calcium isotopes. So there is really a strong link between lactation and calcium isotopes. We also want to investigate if there is an effect of egg laying on calcium isotopes, because you can see here it's some values for a chicken, and with some values also for the eggs of this chicken. And the isotopic composition of the egg is different than the one of the adult. So it might be, technically it might trigger an effect on the isotopic composition of the adult. So this is something that we want to investigate. And we also want to investigate what happens when we mix both lactation and egg laying, which is the case for modern monotremes. So that it's mainly to study these animals that I am here in Australia for 3 months, is to see what is the isotopic composition of this animal and how we can have information on their reproductive strategies, so on both egg laying and lactation. The aim of doing that is that this mixing of egg laying and lactation is suspected to be also the same reproductive strategy adopted by mammal ancestors and by mammal-like reptiles. And so, for the moment, there is really few evidence on which was the reproductive strategies of these mammal-like reptiles. So this is something that have been a lot of debates debated, but for the moment we don't have direct evidence of anything for their reproductive strategies. So that's something that will be really interesting to investigate. So my PhD question are to investigate the effect of different reproductive physiologies on the calcium isotopes in adults but also in juveniles, in order to improve our comprehension of the calcium isotope systems. thanks to that, we could improve also our diet modeling for past diets and also to better understand the past trophic structures. And the main goal is to constrain more precisely when the lactation occurred among mammal ancestors and what was the evolution of this group and of this biological trait. And depending on our data, it could be also possible to develop a method to identify the sex among fossils, which is also something that is really debated and really complicated to do with conventional methods. So thanks for your attention, and if you have any question, don't hesitate to ask.